There is a building sitting in the south of France that has been standing for 800 years. It has survived the Black Death. It has survived wars that erased entire kingdoms. It has survived the French Revolution, 2 world wars, and every storm that the Mediterranean could throw at it for 8 centuries. And for every single one of those 800 years, not one person has touched its heating system. No one has adjusted its climate controls. No one has repaired its humidity regulators. No maintenance team has ever been called. No sensor has ever been replaced. No thermostat has ever been calibrated. Because as far as official history is concerned, it doesn't have any of those things. And yet, step inside that building on the hottest day of August when the Spanish border towns nearby are hitting 42 degrees Celsius and the air inside is cool. Not air-conditioned cool. Something different. Something older. The stone itself seems to breathe. Step inside in January when the tramontane wind comes down off the Pyrenees and the streets outside are brutal. And the interior is not warm, but it is not freezing either. It holds. It resists. The building is Girona Cathedral, and what is happening inside of it is not a miracle. It is engineering. In 2022, a team of building physicists published a study in the journal Energy in Buildings. They placed sensors throughout Girona Cathedral and monitored it for an extended period, measuring temperature, humidity, airflow, and thermal response. What they found stopped them cold. Outside the building, daily humidity could swing by 60%. Inside in a building with no mechanical systems, no insulation, no modern climate control of any kind, the variation was 5%. The thermal lag between the outside world and the interior of the cathedral was approximately 1 month, not 1 day. 1 month. They praised this as an ideal environment for preserving medieval artwork. A perfect, stable microclimate, a happy accident of history. But here is the thing. I don't think it was an accident. I think someone designed it. And if they designed the climate control, what else did they design? What else is hiding inside these buildings that we have been looking at for centuries without actually seeing? Welcome to the Vertical Archive. I document the things that built civilization and the things civilization forgot. Today, we're going inside the most studied buildings in human history, and we're going to find something that has been hiding in plain sight for 800 years. Stay with me, because this one gets deep. What we think we know, let me tell you the official story first, because it's not wrong. It's just not complete. Between roughly 1140 and 1500, at a period we call the High and Late Gothic medieval Europe, went on the most extraordinary building binge in the history of architecture. In a span of 3.5 centuries, craftsmen without calculators, without structural engineering software, without cranes, without steel, built structures that have never been surpassed for their combination of size, structural audacity, and environmental intelligence. We're talking about buildings with stone vaults spanning 20, 30, sometimes 40 meters overhead. Walls dissolved almost entirely into glass. Structures so tall and so thin that modern engineers, when they first analysed them with computer modelling, assumed there had to be some mistake, that these buildings shouldn't still be standing. And the official story says, faith drove this. The ambition of bishops. The pride of cities competing with one another for the tallest spire, the widest nave, the most dazzling rose window. Trial and error, guided by master builders who passed their knowledge through guilds and apprenticeships. That story is not wrong, but when you sit with it long enough, paradoxes start to emerge, and once you see them, you can't unsee them. Paradox 1. The complexity problem. We are asked to believe that societies operating with so-called primitive tools, no calculus, no formal structural analysis, no material science, somehow intuitively produced buildings whose engineering, when analysed by modern computers, turns out to be precisely optimal. Not approximately optimal. not close. Precisely, the Cathedral of Girona, the same building we started with, has the widest stone vaulted nave ever constructed in the history of the world. When researchers ran its buttressing system through modern geometric stability analysis, they found it adhered to the principles with a level of precision that, frankly, should not exist in a structure built by intuition and faith alone. Someone did math. Real math. Maybe not the kind of math we recognize, but systematic, transmissible, precise knowledge about forces, loads, and the behavior of stone. We just don't know where that knowledge came from. Or rather, we keep forgetting to ask. Paradox 2. The water problem here is the paradox that I want you to hold in your mind for the rest of this video. For a stone building, water is the primary enemy. Water seeps into cracks, freezes in winter, expands and over decades destroys the hardest stone. Every engineer who has ever worked on a historic masonry building will tell you the same thing. The number one priority is drainage. Get the water off the building. Get it away from the foundations. Fast. And the cathedrals do this. Aggressively, elaborately, with a level of engineering investment that goes far beyond what simple waterproofing logic would require. Notre Dame de Paris has a roof area of over 10,000 square meters. In a heavy rainstorm, that roof collects tens of thousands of liters of water. The system designed to handle that, load the gutters, the channels, the gargoyles, the underground infrastructure, was not bolted on as an afterthought. It was designed in from the beginning, integrated into the very structure of the building. The question the history books ask is, how did they manage the water problem? The question I want to ask is different. What if water wasn't the problem? What if water was the resource? What if the elaborate, oversized, over-engineered water management systems of Gothic cathedrals weren't built to get rid of water, but to collect it, direct it, store it, and use it? What if these buildings are not just churches? What if they are, at their core, machines? To find out, we need to go to the roof. The capture basin every major Gothic cathedral in Europe charters: Notre Dame, Amiens, Cologne, Canterbury. Salisbury, Santiago de Compostela was roofed in lead, not clay tile, not slate, not wood shingle. Lead. Stop and think about what that means for a moment. Lead in the medieval period was extraordinarily expensive. Mining it required significant infrastructure. Smelting it required specialized knowledge. Transporting it, because lead is dense, heavier than almost any other building material, was a logistical challenge. And applying it to a roof hundreds of feet in the air, on a structure that was still being built, required skilled craftsmen who commanded high wages. So why lead? The official answer is durability. Lead doesn't rust. It doesn't crack under freeze-thaw cycles the way tile does. It is self-sealing. A small scratch or gap closes over time as the metal slowly deforms under its own weight. A well-laid lead roof, properly maintained, can last for centuries. Notre Dame's original lead roof, before the 2019 fire, was estimated to be largely original, 800 years old. This is true, but it is not the whole truth. Lead has another property that is not usually mentioned in architectural histories. From a hydrological perspective, lead is a near-perfect membrane. It is essentially impermeable to water. Unlike tile or slate, which allow a small percentage of water to filter through gaps or be absorbed into the material itself, lead captures everything. In a heavy rainstorm on a lead roof cathedral, the runoff efficiency approaches 100%. Every drop that falls on that roof becomes available water. Now, if you are a medieval builder and your primary concern is keeping the interior dry, lead is a good solution. Expensive, but effective. But if your goal is to harvest the maximum possible volume of clean rainwater from a massive elevated surface, lead is the only logical choice. There is no other material that performs better. Lead is not just a roof covering. Lead is a collection membrane. The Roman Precedent. This is not a new idea. The Romans understood lead and water better than almost any civilization before or since. They used lead pipes fistulae plumbae throughout their water distribution systems. They lined their aqueduct channels with lead to prevent seepage. They used lead cisterns to store collected rainwater in regions without reliable springs. The knowledge of using lead as a water harvesting material was not lost in the medieval period. It was inherited. The cathedral builders were working in a tradition that went back 1,000 years. What they did was scale it up to an industrial level. A single cathedral roof could collect, in a moderate rainstorm, enough water to supply a small town. Where did that water go? To answer that, we need to follow it down off the roof and onto the most misunderstood structural elements in the history of architecture. The scale of what we're talking about before we move on, I want to make sure you have a sense of scale here, because it's easy to throw around a number like 10,000 square meters and have it not mean anything. 10,000 square meters is roughly the size of 1.5 football pitches. Imagine a football pitch, and then imagine that entire surface as a lead-covered funnel, elevated 30 or 40 meters above the city, perfectly engineered to capture rainfall and direct it with precision. In Paris, the average annual rainfall is about 640 millimeters. Applied to a 10,000 square meter roof, that is 6.4 million litres of water per year. 6.4 million litres. From a single building. In a medieval city, a city without reliable municipal water supply, where water was a daily survival concern, where disease outbreaks were often linked to contaminated ground sources, 6 million litres of clean gravity-fed rainwater, collected on a stone and lead surface high above the street, was not a nuisance. It was a resource. And the builders knew exactly where to send it. The Buttresses, aqueducts in plain sight, the flying buttress, is one of the most famous structural innovations in the history of architecture. And the story we tell about it is almost entirely structural. Here is that story. Before the Gothic period, stone church walls had to be thick and heavy to support the weight and lateral thrust of stone vaults above. Thick walls meant small windows. Small windows meant dark interiors. The flying buttress, an arched structural support that reaches out from the wall like a stone arm. Transferring the thrust of the vault to an outer pier changed everything. Suddenly the wall was freed from its structural job. It could dissolve into glass. The Gothic interior, flooded with coloured light, soaring and ethereal, became possible. This is a true and accurate account of what the flying buttress does structurally. It is not a complete account of what the flying buttress is. The gutter nobody talks about walk up to any major Gothic cathedral. Not just the famous ones, any Gothic church with flying buttresses. Find one that is not too heavily restored. Look at the top surface of the buttress, the upper face of the arch that reaches out from the wall. It is carved into a channel. Not accidentally, not incidentally. Deliberately, the top surface of a flying buttress is almost universally shaped as a gutter, a concave channel that slopes from the wall outward toward the tip of the buttress. Water from the roof is not sent straight down the side of the building, where it would pool at the foundations and cause exactly the kind of long-term damage that kills stone structures. Instead, it is directed outward onto these elevated channels and carried away from the structure entirely. In other words, the flying buttress is simultaneously a structural support and a water aqueduct. One element. Two critical functions. Built as a single piece of stone. I want you to stop and consider what this tells us about the people who designed these buildings. A modern building project would have a structural engineer and a drainage consultant. They would produce separate drawings. They would probably have arguments about whose solution takes priority. The flying buttress says, we solved both problems with one element. We didn't separate them. We didn't even see them as separate problems. That is a level of integrated thinking that most of our modern construction industry has lost entirely. The cathedral in the rain, if you have ever seen a Gothic cathedral in a genuine downpour, Not a drizzle, but a real storm. You have seen something that almost nobody describes in architectural histories. The building comes alive. Water pours off the roof, hits the channels at the top of each buttress and moves fast. Purposeful, directed along these elevated stone aqueducts. During a heavy storm, every one of the dozens of flying buttresses on a cathedral like Amiens or Chartres is carrying a running stream of water. Not trickling. Running, this is not drainage. This is water management. There is a difference. Drainage is passive. You slope a surface and water finds its way off. What these buttresses do is active. The water is being directed with precision, controlled, channeled to specific points. And at those specific points, it meets the most famous and most misunderstood element of Gothic architecture. The hydraulic nozzle, called a gargoyle, the word gargoyle, comes from the Old French gargouille. It means throat, not demon, not monster, not decoration. Throat, a functional word for a functional object. The history books will tell you that gargoyles are decorative water spouts designed to project rainwater clear of the building's foundations. This is true. But calling a gargoyle a decorative water spout is like calling a jet turbine a spinning fan. It's technically accurate and completely misses the point. Let's analyse the gargoyle as what it actually is, a hydraulic nozzle. Water is collected from a massive roof. It is channeled along the sloped gutter of a flying buttress, gaining velocity as it descends the slight grade. It then enters the body of the gargoyle, a narrowing channel, like the barrel of a pipe, and exits through the open mouth. The elongated neck of the gargoyle is not decorative. It is a velocity chamber. The long, narrowing form accelerates the flow and directs it as a coherent jet, projecting the water several meters clear of the building's base. This is nozzle physics. This is the same principle used in fire hoses, irrigation systems, and industrial water cannons. The medieval builders may not have had the vocabulary of fluid dynamics, but they had empirical knowledge of it, and they built it into stone. But here's the thing that has always bothered me about the gargoyle explanation. As a drainage system roof, buttress, gargoyle is an open loop. Water comes in, water goes out. Everything is discarded. If the goal is just drainage, this system is effective, brilliantly effective. But it doesn't explain everything we find around cathedrals, because some of the water, not all, but some doesn't just fly into the street and disappear. Some of it goes down. Below the surface, the hidden infrastructure medieval cities are layered. Every major European city that has been continuously inhabited for 1,000 years has, beneath its streets, an archaeology of infrastructure pipes, drains, foundations, vaults that tells a story the surface never reveals. When researchers began doing systematic ground-penetrating radar surveys and excavation work around cathedrals in the latter half of the 20th century, they found something that didn't quite fit the narrative. They found water infrastructure, not the incidental drainage channels you would expect around any large building. Deliberate infrastructure culverts, distribution channels, and in several cases, cisterns. Underground water storage tanks positioned at the base of these buildings, connected to the drainage systems above. This is not widely discussed. You will not find it in most popular histories of Gothic architecture, but it is in the scholarly literature if you know where to look, and if you read these findings not as isolated curiosities, but as part of a pattern. The Constantinople Precedent, 500 years before the first Gothic cathedral was built, an emperor in Constantinople ordered the construction of a chamber beneath the city. The Basilica Cistern Yerebaten Sank in Turkish, the sunken palace, was commissioned by Justinian I in 532 AD. It sits beneath the city of Istanbul, its 336 marble columns rising from the dark wall, its barrel-vaulted ceiling stretching into shadow. At full capacity it could hold 80,000 cubic meters of water, 80 million litres, enough to sustain the population of Constantinople through a prolonged siege, and it sits directly beside the Hagia Sophia. Not coincidentally, the connection between the greatest place of worship in the Christian world and the city's critical water infrastructure was not accidental. It was designed. The Hagia Sophia and the Basilica Cistern were part of a single integrated urban system. This is the precedent. The technology for building vast underground water storage beside a major religious structure existed and was operational 5 centuries before Gothic architecture began. The knowledge didn't disappear. It travelled. How the knowledge travelled west the Crusades are usually taught as military history, but they were also the greatest technology transfer event of the medieval world. Generations of European engineers, builders, and architects spent time in the eastern Mediterranean in Byzantium, in the Levant, in cities where Roman and Byzantine water infrastructure was still operational. They saw aqueducts. They saw cisterns. They saw buildings that managed water on a civic scale. The Knights Templar, who became major financial patrons of cathedral construction across France and beyond, maintained a permanent presence in Jerusalem for nearly 2 centuries. They lived above one of the most sophisticated underground water systems in the ancient world, the vast cisterns beneath the Temple Mount, some dating back to the Iron Age, were known to them. Some historians believe the Templars not only knew about this infrastructure, they documented it. What they brought back to Europe was not just relics and stories, it was knowledge. Engineering knowledge. The kind that doesn't appear in theological manuscripts, but shows up carved in stone over the following 2 centuries. The underground infrastructure around Gothic cathedrals is not a mystery once you situate it in this context. It is the Western expression of an Eastern tradition, the integration of sacred space and water infrastructure that had been standard practice in the Mediterranean world for 1,000 years. But even this, the roof, the buttresses, the gargoyles, the cisterns, is not the most sophisticated part of the system. For that, we need to look at the walls. The breathing wall, where the real intelligence is, we think of stone walls as solid. Impenetrable, we think of a cathedral wall as a fixed inert mass stone and mortar, dead and static. This is wrong. Historic masonry stone set in traditional lime mortar, the kind used in every Gothic cathedral, is not solid. It is porous. It breathes. Lime mortar is a material of remarkable physical intelligence. It is permeable to water vapour. It is flexible under thermal stress. It is self-healing over time as the calcium carbonates slowly recrystallize. It is the opposite of modern Portland cement, which is rigid, impermeable, and eventually fails catastrophically. The walls of a Gothic cathedral are not a barrier between inside and outside. They are a membrane. And like all membranes, they absorb and release moisture in response to the conditions on either side. This was known. The master builders knew their walls breathed. They designed for it. They chose materials specifically because of this behaviour. The question is whether they simply accepted this property as an unavoidable characteristic of the materials, or whether they deliberately exploited it. I believe they exploited it, and the evidence is in the physics. The thermal battery principal water has the highest specific heat capacity of any common substance. What this means in plain language is, water resists temperature change more than almost anything else. It takes an enormous amount of energy to heat water up, and it releases that energy very slowly as it cools down. This property thermal mass is why bodies of water moderate coastal climates. The sea heats slowly in summer and cools slowly in winter, stabilizing the temperature of the land around it. It is one of the most powerful passive thermal management mechanisms in nature. Now imagine that property embedded in a wall. Not a small wall, a wall 2 meters thick, 10 meters tall, running the full perimeter of a building the size of a city block. A wall that is not just stone, but stone holding water. Not pooling water, not flooding water, just moisture. The steady, distributed presence of water in the pores of the stone and mortar. That wall is a thermal battery. In summer, as outside temperatures climb, heat tries to move through the wall into the building. But instead of simply warming the stone, which would rapidly heat the interior, the energy is consumed by a different process: the slow evaporation of the moisture held in the wall's pores. This is evaporative cooling. The wall doesn't just resist the heat, it eats it. The energy that should have become heat inside the building is instead converted into the phase transition of water from liquid to vapor and released into the atmosphere outside. This is air conditioning, not metaphorically. Mechanistically, the same physical principle that makes a wet cloth feel cool on your forehead is operating at architectural scale across thousands of square meters of ancient stone. In winter, the process reverses. The moisture-laden stone releases its stored thermal energy slowly, buffering the interior against the cold, not warming it dramatically, but moderating the extremes, keeping it livable. The 2022 Girona study, What the Numbers Say Let's Go Back to Girona. Because the numbers from that 2022 study deserve more attention than they have received. The researchers found a 1-month thermal lag between exterior and interior temperatures. Think about what that means. The stone walls of Girona Cathedral are so massive, so moisture-laden, so thermally capacitive that it takes a full month for a change in outside temperature to be felt inside the building. The wall is not just resisting the heat, it is delaying it by 30 days. For a medieval community that used this building not just for worship, but for shelter, for meetings, for storing food and medicine and important documents, this was not a luxury. It was survival infrastructure. The humidity results are even more striking. A 60% swing in outdoor humidity, producing a 5% variation inside, is a performance ratio of 12:1. Modern climate-controlled buildings in museums and libraries facilities specifically designed with precision humidity control, with mechanical dehumidifiers and humidifiers running continuously, often target a variation of less than 5% for art preservation. They achieve this with active mechanical systems, energy consumption, and constant maintenance. Girona Cathedral achieves the same result with 800-year-old stone and no moving parts. The researchers who published this study framed it as a fortunate side effect, a passive climate system that emerged from the building's construction as a happy accident, now usefully repurposed as a conservation environment for medieval art. I think they were wrong to call it an accident. I think they were observing the designed behavior of a system that someone built deliberately. I think the builders of Girona Cathedral understood, at some level, whether through mathematics or empirical tradition or inherited knowledge, we can no longer trace that a massive, moisture-laden stone wall could moderate climate. And they built it that way on purpose. The system ASA whole, what they actually built, let me put it all together. Because when you see the individual components in isolation, you can always find an alternative explanation. The lead roof, just durability. The buttress gutters, just practical drainage. The gargoyles, just decorative waterspouts. The underground cisterns, just coincidence. The breathing walls, just a happy accident. But when you see them as a system, when you trace the movement of water from the sky all the way through the building and into the ground, the coincidences stop being convincing. Tracing the water rain falls on the lead roof, a near-impermeable membrane with the surface area of a football pitch and a half. The water is captured, almost all of it, with almost no loss, and directed toward the roof gutters. From the roof gutters, the water moves outward onto the flying buttresses. These stone arches, which are simultaneously structural supports and elevated aqueducts, carry the water away from the building at height, preventing it from running down the walls. At the end of each buttress, the water meets a gargoyle, a hydraulic nozzle, shaped to accelerate the flow and project it as a coherent jet away from the foundations. But not all of it ends there. Around the base of the building, there is infrastructure channels, culverts, collection points that captures some portion of this water and directs it underground. To cisterns, to storage, and meanwhile the walls themselves massive, porous. Moisture retaining are performing their own work, absorbing atmospheric moisture, holding it in their pores, using it as the medium of a passive climate control system that has operated without interruption or maintenance for centuries. This is not a building with a water management system attached to it. This is a building where water management is foundational to the design, where water is not the enemy to be expelled, but the medium through which the building performs its most sophisticated functions. What does this mean? It means we have been fundamentally misreading these buildings. We have read them as theology, and they are. We have read them as art, and they are that too. We have read them as structural engineering, and that reading is correct. But we have not read them as environmental machines, and that, I believe, is what they primarily are. The builders of the Gothic cathedrals did not see structure, water management, climate control, and human comfort as separate disciplines to be solved by separate specialists. They saw one problem, and they built one solution. Every element serves every other element. The structure enables the water management. The water management enables the climate control. The climate control enables the human occupation that makes the building meaningful. It is a closed, integrated, self-reinforcing system. And it works. 800 years later, it still works. With no maintenance, no energy input, no replacement parts. We have not built anything like it since. The lost paradigm, what we forgot A&D, why it matters, I want to end with the question that I cannot stop asking. We did not lose this knowledge because we lacked the intelligence to preserve it. We did not lose it because some disaster erased it. We lost it deliberately, or rather, we dismantled the system that carried it. The guilds. The generational transmission of embodied, practical, empirical knowledge that could not be written down because it lived in hands and eyes and the accumulated judgment of decades of practice. When that system was broken, and it was broken systematically by industrialization, by the professionalization of separate disciplines, by the reorganization of construction into specialized trades that no longer speak to each other, the knowledge went with it. We did not lose the ability to build a cathedral because we lack the tools. We have tools that would have seemed like divine magic to a medieval master builder. We lost the ability because we dismantled the thinking that made the building possible. The integrated, holistic, cross-disciplinary wisdom that refused to see structure and water and climate and human experience as separate problems. We are now, very slowly, beginning to rediscover it. The field of bioclimatic architecture, designing buildings that work with natural forces rather than against them, is finding in these ancient structures a performance benchmark that modern construction has not yet matched. Researchers are publishing papers about the thermal performance of Gothic cathedrals. Engineers are studying gargoyle geometry as a model for passive drainage systems. Material scientists are re-examining lime mortar as a superior alternative to Portland cement. The stones haven't changed. The physics hasn't changed. The knowledge is still there, encoded in every flying buttress and every breathing wall, waiting for us to ask the right questions. The vertical archive exists because these questions matter. Because the things we've forgotten are often more important than the things we think we know, and because the greatest secrets of history are usually not hidden. They are carved in stone, standing in every major city in Europe, and we walk past them every day without seeing them. What else is hiding in plain sight?